Alright, good afternoon, everybody. Hope you're doing well. Hope your weekend was good. And if you started WSU, hope you're off to a good start there. And your other classes at Clark are probably wrapping up in the next few days. So if you got exams in there and stuff, hope you're feeling prepared for those. And this is our last lecture for Engineering 270. So we're going to talk about stuff we've done, Lab 6, Homework 7, Homework 6, all sorts of things like that. And then, hopefully lots of questions from everyone on whatever we've been going through. I'll make a few comments about the final exam, and then we're going to go on. We're just going to start picking up topics that we haven't gotten to yet. Including talking about floating point, talking about computer architecture, memory design, performance, concurrency, networking, whatever we can fit in probably about 3 hours. I'll probably talk until about 3. I won't do a full 4 hours on you, but I'll probably go until about 3 o'clock, and then I'll be online in the 270 Zoom room if anybody is still working on labs or has questions about anything. Alright, so can someone shoot a chat message and at least let me know that you can hear me talking?
We can hear you.
Cool, awesome, thank you. Alright, I have a very new setup. So Clark has, been planning for some time to be online for fall. The word I just got is you're going to be online for winter also. At least the classes I'm teaching will be. So this is a setup that will continue for a while. So upgrading my microphone and camera and figuring out the nuances of Zoom. Alright, so before I jump into all of that, any questions, anything anybody wants to talk about or ask about up front? Alright, well, let's start with the last homework. So the homework that I graded and posted back comments on was homework 6, which was related mainly to timers and the timing subsystem and the A to D subsystem. So I looked at the majority of these questions. So I looked at questions 84 and 85, and if you can do those, then presumably you could do 82 and 83. So 84, you wanted to use timer 1 to set up a 10-second delay and show the values for T1 con and for the timer registers as well. And so the procedure is something like this. So if we stick with a 16-bit timer, our timer registers are going to overflow when they count up to 65,536. Now it depends what kind of clock you're using. If you're using the default 8 kilohertz clock, if you're using 1 megahertz clock, and so on, you're going to get different answers. Most people went with the 8 kilohertz clock, which was what I was kind of had in mind, because that's the one we talk about most. So 8 kilohertz. So we're starting with a 32 kilohertz system clock. Okay, it's actually 31, but we usually do 32 because it divides easier. Divide that by 4, you get an 8 kilohertz instruction cycle clock. So 8,000 instructions per second. And all things being equal, meaning prescalar of 1, will increment our timer register 8,000 times a second. Alright, so if we want a 10-second delay, that's 80,000 instruction cycle ticks that we need. and we can't load a value into our timer register such that after 80,000 ticks it hits the overflow level for the first time. So we have to use a prescaler. So if you use a 1 to 2 prescaler, then we only need 40,000 well, 10-second delay, we need 80,000 increments. Alright. 80,000 instructions. If we use a 1 to 2, 80,000 instructions will give us 40,000 increments. Alright, because every other instruction increments our timer. If we use a 1 to 4, then we only need 20,000 increments. If we use a 1 to 8, then we need 10,000 increments, and so on. So your prescaler basically increases your time before an interrupt occurs. Now, in general, we'd like to use the smallest prescaler possible, right, for reasons of accuracy. If we used a prescaler that was so huge that we only needed, 5 increments, that's an issue of granularity. Right? If it's taking 8 instructions to increment this once, but we do the math and maybe we really want 6 instructions to cause an overflow, well, we can't specify that. We can specify multiples of 8. So we usually use the smallest prescaler possible, but a 1-to-1 prescaler is too small. We need to somehow count up 80,000 things. So if we went with a 1 to 2, we want 40,000 increments. And so what will we put in the timer 1 register? 65,536 minus 40,000. So 25,536. For a 1 to 4, we want to subtract 20,000. So it's 45,536. For a 1 to 8, we want to subtract 10,000. So it's 55,536. And so the pattern you're seeing is that the larger this number, the shorter the time interval, right? Because we're closer to the overflow point. So that's sometimes counterintuitive. All right. So depending on what prescaler you picked, right, you figure out the value to load into timer 1 H&L to cause a 10-second delay. 87, what's the shortest possible time interval? Well, it's basically 1 instruction. So depending on what your clock is, if your clock is, again, the 32 kilohertz system clock, your shortest time is 1/8000th of a second. Some people figured out what the fastest clock speed was that you could put in, which is there's an 8 megahertz clock built in. Divide by 4, you get a 2 megahertz instruction cycle clock. That's half a microsecond, so that would be the shortest timing period in that case. The longest time interval possible, we talked about this last time, so set up your prescaler as big as possible and start off your timer at 0. Make sure you're in 16-bit mode, so it takes full 65,000 instructions or 65,000 increments to overflow, with a large prescaler to pack as many instructions as possible per increment. So an 8-to-1 with 64K comes out to about 65 seconds. Now remember, you can put your own clock into the chip. You can drive it from an external clock. So I mean, you could put in a clock that ticks once per second and make this a really long delay if you wanted. There's lots of possibilities like that, but just using the built-in timer. Mostly what I wanted you to think about was what are the knob settings that you can use in terms of prescaler and initializing timer high and low. Alright, so I looked at 88, I looked at 89. Again, if you're an 8,000th of a second per instruction, use a prescaler of 1 and set PR2 equal to 8. And you should get an interrupt after 8,000th of a second, that's 1 millisecond. 92, shortest time interval possible with timer 2. Again, it's an 8,000th of a second. Longest, so this one you have to multiply out the prescaler and the postscaler. And the largest number of ticks you can have before an overflow is 256. And if you multiply all that out, you end up with about 8 seconds. Which is why the answer to 91 is you can't do it. You can't get a 10-second delay out with a 32 kilohertz clock. Alright, 94, write some PIC code to toggle an LED on pin 18 approximately every 2.5 seconds. So, so this was only one point like these other questions, but a fair amount of work. So you got to wire up the interrupt subsystem. You got to configure pin 18, which is RB3, bit 3 of port B, to be an output. You've got to have code at location 8 or 18 to vector to your interrupt handler. You've got to have code at location 0 to jump to your main code. Do your setup, go into a branch, right, the usual drill. And you have to set up timer 1 to cause an interrupt every 2.5 seconds, or, you know, it may be interrupt every half second and count every 5th interrupt. Go ahead and toggle the pin. Lots of flexibility on how you want to do that. Alright, and then sketching some waveforms. Everybody got these right, so 50, 90, 10, 100, 0, duty cycles, yes, those are all pretty straightforward to draw. So 50 is even, 90 is mostly on, 10 is mostly off, 100 is always high, 0 is always low. Alright, so someone commented, new mic sounds good, excellent, glad to hear it. And just trying to know if you're recording this lecture already. Yes, I am. As far as I know now, everything is in flux, because I keep moving things around, but I should be recording. But hey, you never know. Alright, and then the analog digital stuff. So sketching a waveform from 0 to 4 volts, saw some interesting waveforms. The idea here was to look at different voltages in this waveform and see what bit values those correspond to. If you only have a 2-bit A to D, you've only got 4 possible voltages you can represent. So 0 to 4 volts, it's pretty coarse, right? You're going to have a lot of voltages that correspond to the same bit pattern. So this was walking you through sort of, you know, exploring those boundaries. And then in the last question in this section, looking at the voltage range assigned to each 2-bit value. So basically 0 to 1 volt would be 0, 1 to 2 would be 1, 2 to 3 would be 2, and 3 to 4 would be 3, if you looked at those 2-bit numbers. And then changing the high and low of our voltage range. So if we go, instead of 0 to 4 volts, from 1 to 5 volts, or from -2 to 2 volts, right, the assignment of bit patterns to voltages changes, but the resolution doesn't change. The number of buckets is still the same, 4 buckets in this case, and the range of voltages for each bucket is still 1 volt. Alright, and then 115, in these two cases, right, where you have different ranges but it's still a 4-volt range, if you pick a particular bit pattern like 1, 0, what's the range, the largest minus the smallest voltage corresponding to that bit pattern? And a bunch of people suddenly jump to a 10-bit A to D here, and I'm not sure why. I guess that was worded confusingly. But I was looking at the exact same questions from here and here, picking a single bit pattern like 1, 0, and saying what's the range of voltages corresponding to that. So from 1 to 5, right, 0 would be 1 to 2, 1 would be 2 to 3, 1, 0 would be from 3 volts to 4 volts, right? The range of that is still 1 volt, 4 volts minus 3 volts. From -2 to +2, 1, 0 will correspond to the range 0 volts to 1 volt. Well, the range of voltages in that, largest minus smallest, is still 1 volt. Okay, that's the notion of resolution. And it has nothing really to do with where the actual high and low voltage are. It has to do with what the difference is between the highest and lowest voltage and the number of bits. And then if you increase that scale, that high and low voltage limit from 0 to 8, now your range is 2, and from 0 to 8,000, your range is 2,000. Right? So just the idea that your resolution gets really, really poor if your possible input range gets really large and your number of bits is small. So now we start increasing the number of bits. We go to 3 bits, and if you write out the range from 0 to 4 volts, you'll find that each bit pattern corresponds to a half volt range, 0 to 0.5, 0.5 to 1, all the way up to 3.5 to 4. So your resolution in this case is a half volt. And then in here we go to 4 bits, and our resolution increases to 0.25 volts. And with 5 bits, it gets even better at 0.125 volts, so 1/8 of a volt. And then for n bits, it's going to be 4 over 2 to the n. That's the pattern that you get from looking at these. And then if you go up to 40 volts, your resolution will go up by 10. So if your resolution was 0.125 volts here, now if my inputs go from 0 to 40, my resolution is down to 1.25, 1.25 volts. Right? 5 bits, you're breaking your input range into 32 bins. So if my voltage goes from 0 to 40, 32 bins, well, each bin is bigger than a volt. Alright, so that was exploring those notions. And then I didn't grade you on the ADCON registers, because those you just read from the data sheet and set up. And if you don't do it right, it doesn't work, and you read it again and you set it up. And your 10-bit conversion value just comes out in AD result high and low. I'm not going to ask you to do AD stuff on the exam. So. All right, questions on Lab 6? Did it mostly work for people?
Yeah, I got it to work, but I had a few workarounds.
Okay. MP Lab is an interesting piece of software. It's all done in Java. It's using a window managing system called NetBeans, which is a nice system. If you've done 223, it's an alternative using like Window Builder. And they've done a pretty good job of making it full-featured, but still work. But it's definitely got some quirks. And as you probably found, a chunk of doing Lab 6 was figuring out how to, deal with the occasional crashing of Java. One person typed in "Hello World" in their data file, but they used an editor that actually tried to be smart, and the opening quote was different from the ending quote. So it used a Unicode character set, so that the quotes would be slanted in the right direction. And man, that confused the heck out of MP Lab. It was reporting like Java internal errors every time that they tried to look at their UART output. So that was interesting. And this is something that happens. MP Lab is free, but even with commercial software, sometimes you just run into the weirdest issues, and that's just kind of part of dealing with technology. It's a moving field, and something might make perfect sense on paper, and you're all set to use it, and then you find yourself debugging a piece of software that your company paid for the first week of an assignment. So that happens sometimes. So real world experience. All right, homework 7, indirect registers. So you're going to see an indirect register question on the final. So I will get these graded and get some feedback to you. We're not going to have a chance to really talk in detail about particular things I see. So if you're not absolutely 100% sure that you did these questions correctly, let's ask questions about them and let's go through them.
Can we just go over one of them?
Which one?
Post-deck 0.
Post-deck 0, okay, so like 136?
Yep.
Alright, so write some pick code which clears file registers 10 through 20. Using indirect file 0 and file select register 0. Alright, we want to use post-deck. So, well, let's do this in MP Lab. This way you know if I'm lying to you. Alright, so we want to clear file registers 10 through 20. I'm going to want to put location 10 into file select register 0. So I'm going to use my load file select register instruction. And I'm going to start with location 20 because I'm going to use my post deck. So I'm going to be counting down. So we'll start with file registers 20. And let's see, can we do this nicely? I think we can do this in one loop. I'm going to put a 17 in my W register. I think we're going to want to loop 17 times because 10 through 20 means inclusive of 10 and 20, so that's actually 17 locations. So I'm going to use W to count how many things we want to clear. That's just code, right? The interesting part here is the indirect addressing. So let's go with a loop. Clear F post deck 0. So that should clear the file register pointed to by file select register 0. Alright, and then it should subtract 1 from file select register 0. And I'm going to want to do this 17 times, so I'm going to say decrement file wreg and branch if it's not 0 back to loop. And I'll put a no op here just for kicks. So instead of clearing a file register, let me increment it so we can actually see what happens, because my file registers are starting off at 0. So I'm going to increment, but if I wanted to clear, I would just clear. So let's give this a shot. So I'm sitting here in the beginning, and if I look at my variables, I can see file select register 0 is 0020. Alright, I don't care about this second bank. But I'm pointing to register 20. I'm going to increment that. So register 20 got incremented and FSR changed to 1F. And I'm going to keep doing this. And I'm changing all of my file locations. And my W register up here is equal to 2. It just got decremented to 1, so I'm going to branch once more. FSR 0 is 10, so I'm about to touch location 10. Okay, I've done that. Now I'm going to decrement W register, which is currently 1. When I do that, W becomes 0, and my Z bit turns on, so my branch if not 0 will fail, and I'll fall through to my no op. The interesting part is this statement right here, right, which for us would be a clear. But that one operand does a bunch of stuff, right? It does the indirect addressing based on FSR 0, and then it subtracts 1 from FSR 0. Is that helpful?
Yep.
Okay. What does this code do? I was curious because I wrote it a long time ago.
W register is set to 7 and it just deep counts and then just ends.
Okay. So FSR 0 high is 0, FSR 0 low is 40, 7 goes into W. It increments 40 plus.
W register and FSR O. I think it's L.
Mm-hmm. Yeah, so that should add 40 to 7 and increment what's at that location. So it would increment file register 47. This will subtract 1 from W and then go back and do that again. So it will increment registers 47 down to 41, and then when W becomes a 0, it will skip the branch. So I think it does those 7 locations. And here, again, we loaded FSR 0 high and low explicitly. Oh yeah, you're right, so the high location is 40. No, it's low. Here we loaded high and low explicitly, so we put a 0 into FSR high and a 40 into low. But we can use this LFSR instruction. We could have just said LFSR 0, comma, hex 40. And that loads all 16, actually 12 bits of the file register. So that's what this last question was looking at. And we did a memory block transfer in class on Thursday. All right, other questions? Points of confusion. All right, well, let me talk briefly about the final. I haven't written it yet, but I will do so before Thursday. So best preparation for the final, go through your homework, go through your labs. Okay? This multiple pages of homework questions that we've been working from, these are very typical of the kinds of questions you can expect to see on the final exam. So if you've been doing the homework, if the homework's been making sense, or if you've been having trouble with it but then figuring it out, that's a really good self-assessment for preparation for the final exam. We have not talked about floating point yet. We're going to do that next, but I'm not going to ask you about floating point on the exam either. But I will ask you about indirect stuff. Let's see, another question. Not super confident on the plus W0 command. Yes, so plus W0 is a way to change what indirect register you're talking about without having to change the file select register itself. So I can set the file select register to 40, for example, and it never changes, but I can still access different locations by changing the value of W. And since W is, our most popular register, we have literal instructions for it. We can put things into W easily. Changing W to change what location we want to work with is sometimes more convenient than constantly changing the file select register itself. So yeah, that's exactly what it is. It's a way to, for example, iterate through memory without having to change FSR 0. I had my video displayed in the corner here and it's vanished. That's kind of weird. All right, so final exam. Go through the homeworks, right? Make sure you understand the homeworks. Go through your labs. You've written a bunch of code, you've modified code, you've read code, and you've worked with a number of concepts, right? Including doing I/O, dealing with tri-state registers and the ADCON register, doing bit manipulations, masking off bits, combining bits together in different ways, working with the timers, working with delay loops, working with different pieces of the hardware, right? So be familiar with all this stuff you've been doing in the labs. It's all fair game. I've had some questions recently on delay loops, right? Don't forget about delay loops. Delay loops are another way to do timing. Sometimes we use the timer subsystems, but sometimes you just want to delay 1/10 of a second. Well, if you know you have an 8 kilohertz instruction cycle and you want to delay 1/10 of a second, just do 800 things, right? And that's pretty easy to do. If you make a loop that takes 4 cycles to execute, just do that loop 200 times. If you have a loop that takes 3 cycles to execute, do that 256 times. That's pretty close to 800. That's almost 1/10 of a second. That's the basic delay loop, the decount thing that we've been using in some of the earlier labs. All right, so the exam will be a Canvas quiz. I'm going to set it up to only let you take the quiz once because I had some people who got into trouble with. Anyway, I'm gonna set it up so you can only do it once instead of being able to retake it. So don't submit your final answers until you're done with the exam. Okay, it's going to be set up for a single submission only, and it'll be the same format as last time. There'll be questions listed in the quiz, and you'll either type in your answers or copy and paste images or something. Right, mostly typing in answers. So it'll look like essay questions. They won't get graded automatically. The honor statement question will say you got the answer wrong. Don't worry about any of that, right? And I'll get them graded up Thursday or Friday. Oh, there's a really cute dog outside. Here, I'll show you a really cute dog. Well, it's not so cute when it's tiny. So the quiz, the final, I'm planning on it being a 2-hour exam. I'm going to give everybody 3 hours for it, okay? And if you have extended time allowances, you'll get time and a half on that 3 hours, okay? It's not that I think it's going to take you 3 hours, but I don't want time to be an issue, okay? So I will make the Canvas quiz so that it gives you 3 hours. But don't see the 3-hour time limit and panic that it's going to be a 3-hour exam. I really expect it to be doable in under 2 hours. Okay, but I want to take away the time pressure because I want people to be able to show me what they understand and what they can do with this subject. So you'll have a 3-hour allotment for it, or 4.5 if you have time and a half. All right, any questions about that?
I'm over here.
Okay. All right, let me see something. Yeah, chat's turned on. Okay.
Get out of it.
All right. Well, let's get into the good stuff. So let's talk about floating point. So we've mostly been working with integers, and mostly small integers, 8-bit integers, and there's lots of ways we can represent 8-bit integers, but we've been using sort of the standard way that we learned in Engineering 250 and in CSE 121, which is just weighted positional notation. So if we want to write the number 7, we write it like that. Okay, and it's 2 to the 0, 2 to the 1, 2 to the 2. 1 plus 2 plus 4 is 7. And if we want to write the number 12, we write it like that. 2 to the 2 is 4, 2 to the 3 is 8, 4 and 8 is 12. And then we start to get kind of fancy when we want to write negative numbers. We introduce this thing called 2's complement. So if we write this, that would look like the number 255 if we added up powers of 2, but we see this 1 on the front and we say, oh, this is a negative number. We take the 2's complement, we end up with 1, and so we say this is the number -1. That's our usual way of representing negatives, but there are other ways we could do this. For example, we could use what's called signed magnitude. Which says this is the number +1. That's the number -1. We take this last bit and we just use that as a sign bit. So these 7 bits show us the actual absolute value of the number, the magnitude, and then this tells us whether it's positive or negative. That's really easy to convert, because if you have a number like 12 and you want to make -12, bang, there you go, there's -12. But it's not as convenient for doing arithmetic. You need different hardware circuitry to be able to do things like add positives and negatives if you're using signed magnitude. So the point here is that the way we choose to represent information in binary is kind of arbitrary. Now sometimes we do things a certain way because they make computation easy. Sometimes we do them a certain way because they make the hardware easy to build. Sometimes we do them a certain way because we don't know any better and we're doing this for the first time. But it's more or less arbitrary, right? There's plenty of valid options. And this is even more clear with things like representing letters, right? Why is the binary code for 65 used to represent the letter A? Well, that's just kind of how it is, right? It was chosen by people a long time ago and it stuck. And there were other schemes that were used and they didn't stick. All right, so the question of floating point is an interesting one. Integers are fine. 8-bit integers, we can go from 127 to negative 128. If you're doing astronomy, that doesn't work very well. If you're doing particle physics, 8-bit integers don't get you very far. You need to represent very large numbers and very small numbers, right? We need to be able to represent the distance to a galaxy and the mass of an electron. And if we did this with integers, we would need a huge number of bits, right? 64 or 128 bits maybe. So what do we do on paper when we want to represent a wide range of values that aren't just integers and could be very large or very small? What's the trick that we learn in science class somewhere in school? Scientific notation. So how does scientific notation work? Well, instead of writing a number like 2, 3, 7, 4, 6, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, right? We count how many zeros we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And we could write this as 2, 3, 7, 4, 6 times 10 to the 12th. Or if we're typing this on a system where we don't have exponents and stuff, we could write 2, 3, 7, 4, 6, E, 12. And part of why we do this is that it takes me less physical space to write this number than it did to write this number. A physical space on a piece of paper is similar to memory in a computer. And we could represent this number in integers, but we need a whole bunch of bits, right? Bits are kind of like digits. A bit is a binary digit, bit. So scientific notation is the trick that we use to get away with taking up less space on paper. Well, we can do something similar to get away with taking up less memory in a computer. And remember, when we do scientific notation, there's some rules that we use. One of the rules is we would like to normalize this. We would like to move the decimal point so that we have exactly one digit to the left of the decimal point. And then if we moved over, we adjust the exponent accordingly. So this would be the normalized form of this big, huge number. And if our number was actually something like, if these weren't just zeros, we might still say we're only going to put in 4 digits after the decimal point. Because if you're talking about a number this big, the significance of this digit down here is probably minimal. Now, maybe not. Right? And if you've got like a chaotic system, it may be that, a change of 1 in this least significant digit totally changes the behavior of your system. But in traditional systems that aren't chaotic, right, only these most significant bits tend to be particularly important. So we adopt this convention of saying maybe we'll only have 4 digits after the decimal point. Okay, and we'll always have 1 digit before the decimal point. And we understand that this digit cannot be a 0. Because if we had a number like, 0.4 times 10 to the 12th, we would move the decimal point to make that 4.0 times 10 to the 11th. So that's part of normalizing. Make sure this is a non-zero digit. Alright, we're going to do exactly the same thing, but we're going to do it base 2. We're going to do it in binary. So let's say we want to represent the number 3. So the number 3 in binary looks like 1, 1. And so 3 would be equal to 1, 1 times 2 to the 0. And we have to just kind of remember that we're talking about binary everywhere except for this little 2 down here. But if I got rid of that, I would just say 1, 1 exponent 0. Alright, we want to normalize, so we have to move the decimal point over one spot, so I would write 1.1 exponent 1. And so this would be the normalized form of the number 3.0. Now, how do we write 1.1 in binary? I don't know if we've done this in Engineering 250. We know how to write numbers like 3 in binary. Well, what about numbers that have things after the decimal point? So this is 2 to the 0. This is 2 to the negative 1. So 2 to the 0 is 1, 2 to the negative 1 is 0.5. So 1.1 base 2 is equal to 1.5 base 10. It's 1.5. So 3 is equal to 1.5 times 2 to the first. 1.5 times 2. Not surprising. Alright, what if we wanted to write the number 0.2 using this scientific notation? Well, first thing to do is convert 0.2 to binary. Well, how do we do that? There's a few approaches. We can use the same trick we use to convert integer to binary, but we run it in the other direction. So we can write 0.2 times 2 equals 0.4. 0.4 times 2 equals 0.8. 0.8 times 2 equals 1.6. We throw away the thing to the left of the decimal point and we just carry the fraction part. 0.6 times 2 equals 1.2. Throw away the 1. 0.2 times 2 equals 0.4. 0.4 times 2 equals 0.8. 0.8 times 2 equals 1.6, and so on. Alright, our binary equivalent of this number is formed by these digits that we threw away. So in particular, 0, 0, 1, 1, 0, 0, 1. That's our binary equivalent of 0.2. And you can do a quick sanity check. This would be a half, this would be a quarter, this would be an eighth. If we had a 1 here, we'd have a number at least a quarter, which is too big. But we're starting with an eighth. So 0.125, and this is a 16th, 0.0625. And if you add those together, you get 0.1875. Well, that's pretty close to 0.2. It's a little too small, but we got some other digits we're going to add here. And if we continue this, right, once we had 4 digits, we got back to our 0.2 that we started with. So 0, 0, 1, 1, we're going to have another 0, 0, 1, 1. This is going to repeat. So 0.2 looks like this in binary. Okay, and that's times 2 to the 0, because that's the binary equivalent of 0.2. So how do we normalize? Move your decimal point over 1, 2, 3 spots. And adjust your exponent. Okay, which way do you adjust? Well, if I make this 1 times 2 to the third, I've got a number bigger than 8, right? So when you move your decimal point that way, subtract from your exponent. Right? 1 times 2 to the negative third is 1 over 2 cubed, that's 1/8. 1.1 times an eighth is something slightly bigger than 1/8, right? An eighth is 0.125. So this is the correct value. Alright, scientific notation. If we wanted to represent the negative of this number, the only thing that changes in our scientific notation is we put a little minus sign in the front. Okay, this is signed magnitude representation. We write down the representation for the absolute value of our number, and then at the very end, if our number was negative, we just throw the symbol in the front to say it's negative. We're going to do the same thing in binary. If we wanted negative 0.2, we're just going to say negative 1.1001100110011 times 2 to the negative 3. Alright, everybody with me so far? Binary scientific notation?
Yep.
So the reason we're doing this is because to actually represent a floating point number inside a computer, we're going to codify this representation. We're going to store 3 things. First, we're going to store what's called the sign bit, which is basically, do we have a minus in the front or do we have a plus in the front? 2, we're going to store the exponent. We know we're going to do 2 raised to some power, we're just going to store that power. And 3, we're going to store the fraction, or the mantissa if you want to talk fancy, which is this thing. And we're going to set up a particular way of storing these so that when we look at a bunch of bits in memory, we know which bit is a sign bit, which bits correspond to the fraction, which bits correspond to the exponent. And there's lots of ways we can do that. Right? We can use weighted positional notation to represent this number. We can use 2's complement for negatives. We can store the exponent followed by the fraction. We can store the fraction followed by the exponent. It's arbitrary, right? But it's really convenient if everybody uses the same technique for converting from a floating point number to binary scientific notation to an eventual bit pattern that gets stored in the computer. Why is that convenient? Because I've got a bunch of data that I want to share with you. If my computer and your computer don't speak the same language for representing floating points, I send my numbers over to you and they look like gibberish. And you've got to hire a student to write a converter to change my representation into your representation. And it's a pain. So IEEE, Institute for Electrical and Electronic Engineers, helps with standardization. And they came up with something called IEEE 754. That's the standardization for representing floating point. And you can find this in your textbook. And it's around page 191. So you can reread what we've just been talking about in the text. But here's a good picture of how scientific notation is represented using IEEE 754. So floating point numbers are represented as 32 bits, okay, 4 bytes. The most significant bit, that's your sign bit. A 0 is positive, a 1 is negative. The next 8 bits correspond to the exponent. Now exponents can be positive or negative. And this is a case where we're not going to use 2's complement to represent the exponent. And we're not going to use signed magnitude either. We're going to use something called a biased representation. And the bias simply means we take our exponent and we add 127 to it. That's the 8-bit value that we store in here. So our true exponent that we store is 128 plus the actual exponent we want. So if we wanted to store an exponent of 128, we would actually store the 8-bit number corresponding to 125. Alright, so it's called a biased notation. And then we have 23 bits we can use to store the fraction. Okay, well here's something clever that the people coming up with this did. Remember, when we do plain old scientific notation, we have this rule that we always need a non-zero digit to the left of the decimal point, right? Well, in binary, our only choice for digits are 1 and 0. If we need a non-zero digit to the left, what is that digit going to be? It's got to be a 1, right? So when we normalize a fraction, we always know this digit here is a 1. So we don't actually store that in our scientific notation. We actually start with the thing to the right of the decimal point. And then we understand that the fraction that we're interested in is actually 1 plus the fraction that was stored in this representation.
So they save a bit by doing that?
So they save a bit by doing that. And every bit counts. Right? This is something that we keep bumping into in the PIC processor architecture. Little tricks like using the fact that instruction addresses are always even, so we don't store the least significant bit when we say call or go to. Right? A bit's a bit. Alright, so let's store the number 0.2 as a floating point number. We've already converted 0.2 to binary, and then we normalize it, so we got this pattern times 2 to the minus 3. Okay, so we're going to do positive 0.2. So sign bit is going to be equal to 0 to say we want a positive number. Our fraction is going to be our exponent plus 128. So our fraction is going to be 125, which looks like this, I think. Sorry, that's our exponent. Our fraction is going to be the stuff to the right of the decimal point. 100, 1100, 1100, and so on. Alright, so let's pack it together. What's 0.2 going to look like? It's going to be 0 for our sign bit, 8 bits of our exponent, and then our fraction for the remaining however many bits we have, 23 bits. And so on. Alright, so let's break this up into 4-bit pieces. There's our first chunk, there's our second chunk, there's our third, our fourth, our fifth, our sixth, and this will keep going. Alright, so 0011, oh, hold on a second. Alright, so 0111, that's a 7, 1110 is an E, 1100 is a C, 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 C. So that should be the IEEE 754 representation of 0.2. I messed up. So our bias is 127, not 128. This is actually 127 plus -3. So this should be 124, which looks like that. Alright, that looks better. So 74C, C. It's a repeating fraction, right? It's not exactly equal to this because we need to repeat. Just like 1/3 is not exactly 0.333, this pattern needs to repeat indefinitely. And this is something interesting to think about. 0.2, that's not a weird number, right? That's a pretty common number. In particular, if I was doing banking and somebody gave me $1 for something that cost 80 cents, I would give them 20 cents back. Well, in my computer, if I represent that 20 cents like this, it's not exact. There's a rounding error. And those rounding errors can add up. So this floating point system is really bad for finance. Early computers in the 60s, right, using things like COBOL and stuff, used a totally different method for representing floating point numbers. They used something called fixed point notation. Works great for doing dollars and cents, but not great for scientific calculations. Alright, so it's 1 o'clock. Let's go ahead and take a short break, 5 minutes. Come back, we'll say a few more things, look at some examples of floating point numbers, and then we'll start talking about computer architecture and other topics. Alright, so come back in about 5 minutes, please. Alright, so we're back. Alright. Yeah, I did make a typo here, so it's not my day for binary arithmetic. So 127 plus -3 is 124. This is not 124. This is actually 252. So this should be a 0 in the front. So I went a little bit overboard. So that's what that should look like, and this should be 3E, 4C, C. So that looks correct. But anyway, you get the idea, right? So you're taking your number, you're converting it into this binary scientific notation, and then packing it into this particular representation. And there's different details that we can talk about briefly. So for example, we can also do double precision. Double precision uses 64 bits, so 8 bytes, and still one sign bit. The exponent goes up to 11 bits, so we have 8 times the exponent range. Not a significantly larger range, but look at all the bits we have for the fraction, 52 bits, right? That's huge. That gives us a great deal of precision in double precision numbers, hence the name, right? Slightly larger range, but the main win out is the precision. And so that's useful too. There's a typo in the book, by the way. This should be 3F20, not 10, if you're playing along at home. All right, and detail. When we write things out in scientific notation, we said we always normalize so that we have a single non-zero digit to the left of the decimal point. There's one case where we cannot do that. What's that special case? What number can you not write out with a non-zero digit to the left of the decimal point? It's a special case. How about the number 0? Because the number 0 is just a bunch of zeros. You can't normalize it and never get a non-zero digit to the left of the decimal point, because there are no non-zero digits in the representation of 0. So it's an edge case, and 0 is represented with the following format: an exponent of 0 and a fraction of 0. Okay. If you took this literally as an IEEE 754 floating point number, it would be 1 times 2 to the negative 127th. It's the smallest number that you can possibly represent, smallest positive number, but it's interpreted as being actually a 0 instead of that number, because you got to have a 0, right? That's very important. We can also represent infinity, positive and negative, and that's done with an exponent of 255 and a fraction of 0. So not quite the largest number you could represent, but it's a special pattern that's detected as meaning infinity, and anything with that large exponent in a non-zero fraction is treated as not a number. And these are you know, valid representations of things in this format. And they're useful in various ways. And Java speaks these. C doesn't really, but Java does. All right, so we converted point 2 to 3E, 4C, C, 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 C. Let's take a look at this. So I've got some C code here. Have a floating point number x, which I set equal to 0.2. And then I'm going to print it out and call a print statement. Okay. I'm going to compile this with a -C option, which says don't bother giving me an executable, just compile it to an object. But I'm going to put a switch in there, uppercase S, which means show me the assembly language for this C program. So I'm going to do that, and I've got this main.s, and let's look at that. Well, this is the assembly language version of that program I just showed you. This is not PIC assembly, this is x86 assembly, because I'm sitting on an x86 machine. If I do this on a Raspberry Pi, I'll see ARM assembly, which is closer to the PIC. But this has got these complex instructions like convert SS to SD. I don't know what exactly that does, but it sounds complex. I mean, it's an 8-character opcode, right? Load the effective address of a quad word, stuff like that. And then good old stuff like call. This is calling the printf, right? When you say printf something, you're making a function call in C, and this is where it's actually being called. So somewhere up here, the value of x is being loaded somewhere so that printf knows how to get to that, along with the string x equals %f, which was defined up here, right? These are assembler directives. They don't come down to actual executable code, but they control the assembly process. This is a label. This is a label. This is a directive. This is an actual assembly language instruction. This will get translated to ones and zeros. Move Q moves a quad word. On x86, your registers are things like RSP, RBP. That's a stack pointer and a base pointer. Subtract quad word, move SS, I don't remember, move long, call, move long, and so on. And if we come down here, we find down here at the bottom a declaration. This is like a .equ statement. A declaration of this long number, 104.522.0557. Well, that's a little weird, right? So what's going on with that? Well, let's let me write that down. 104.522.0.557. And let me bring up my calculator and go into decimal, and let's do 104.522.0.557, and let's convert it to hex. Guess what? 3E 4C CCCD. That was our conversion by hand for 0.2, except for this last digit. Well, this last digit, let me write these out. 1100, but what's the next digit after that? It's a 1. Now when you round regular decimal numbers, what's the rule? If you're at 0.5 or larger, you round up. Well, 0.5 is just 1, so if this digit here that we're not going to store is a 1, the rule says round up the digit before it. So this gets rounded up to a 1, 1101, that's a D. So the correctly rounded representation of 0.2 would be 3E 4C CCCD. That's what that long number is that's stored in the assembly language program. So the assembler knew how to do this conversion, did it, and then stored that constant in memory so that our program would have the value of 0.2. Alright, questions about this? Is this making sense?
Slowly but surely.
Okay. Okay, I got my chat window up again. All right. So there's our main program. It runs, it prints out 0.2. Alright, so we know that if we look at this program in VI, it's gibberish, right? But somewhere in amongst this gibberish should be the ones and zeros corresponding to 3E, 4C, CC, CD. Because this program has to contain the value 0.2 so it can assign that value to X and then print it out, right? So let's edit the binary version of this. So this is a hex editor. It brings up something like what you get when you do a hex dump. It shows me the hex code for every byte in my file, and if it's a value that corresponds to an ASCII character that I can print, it'll show me the ASCII equivalent over here on the right. Otherwise it just shows me a dot. This is useful when you want to reverse engineer code or things like that. So let's search. Let's just search for 4C3E. And right up here in my file, there's a 4C, a 3E, a CC, and a CD. Okay, this is not the same order that we originally wrote it out. We wrote down 3E, 4C, CC, CD, but in the file they're stored as CD, CC, 4C, 3E. They're reversed. This is also not standardized. Okay, there's different ways to store things that are bigger than 1 byte into a byte-oriented memory. You can choose to store the least significant bits first or the most significant bits first. And this is something called big endian versus little endian. And again, it's not standardized. One machine may do it one way, another machine does it a different way. You have to constantly convert. Is this a problem? Yeah, this is a huge problem when machines are networked. So when you study networking, you'll learn about host order versus network order. Network order is standardized. Anyway, this is 0.2, these 4 bytes right here. So what if I change that last D to a C and save that, and I rerun my main program? Well, I don't notice that. That's a pretty insignificant change. What if I change this C to a D and I run my program? Well, now we're seeing something different. I just changed this to representation of a different number. Let's put that back to a C. There's 0.2. I'm not recompiling. I'm editing the executable. Okay, how would we represent negative 0.2? What would change in this number to do negative 0.2 instead of positive 0.2?
Definitely a lesser value, I guess.
Okay, how would the bit pattern change?
Would the sign bit would change, right?
The sign bit would change, which is right here. So if I make this a 1 and leave everything else the same, I've represented negative 2. Well, if I make this a 1, this is 1, 0, 1, 1. Instead of the binary representation of 3, what is 1, 0, 1, 1 in hex? That's the letter B. All right, 8 plus 2 plus 1, 8 plus 3 is 11. So if I come over here and I change this 3 to a B, and I'm doing a Control S to save, and now I run my main program, x is equal to negative 0.2. By the way, this is how insecure your computer is, right? I mean, I don't need the source code. I can get rid of that completely. I can get rid of the compiled, I can get rid of the object. Right, so all I have is this one executable in here. And we can totally change what it does by just tinkering with these bits. Right, as long as you understand what the representation is. Alright, so this is how floating point is stored in most computers today. It's standardized, it works well, it's well understood, it's pretty universally supported. Alright, questions on any of that? G-hex is fun to play with, by the way. If you want to start digging into more of this stuff, it's a useful tool to sort of see what's going on. All right. Let's talk about computer architecture in general. And you'll probably take courses in computer architecture if you're computer science bound, possibly if you're double E bound also. Definitely embedded systems. What is computer architecture? Computer architecture is basically studying the design or the architecture of computers, right? So we've been studying the PIC processor. And it has certain characteristics. It's an 8-bit processor. It has a certain number of file registers. It has a certain structure for its instructions. It has 4 timers. It has 18 pins. It runs off of 5 volts, right? There's all these design decisions that were made in coming up with this PIC processor. and there's a PIC 18F1320 instead of a 1220. Slightly different architecture. There's an Intel x86. There's a whole slew of processors in that family. There's ARM processors like you find in a Raspberry Pi or in a cell phone. And computer architecture is this question of how do we design these systems? What choices do we make in designing these? So with what you know about the PIC processor, what are some of the aspects of its design that could possibly have been chosen differently? What are some characteristics of the PIC that we know about that could be something different in a slightly parallel universe?
Are you asking like for improvements or just different?
Improvements or different or whatever. And they can
Maybe more like W registers or something like that.
okay. More W registers. W1, W2, W3, that would definitely be handy. They can be silly changes too. Let's say you're just trying to make your own version of the PIC and you don't want to get sued by the patent lawyers, so you want to make something that's different, so you're going to start changing stuff. Alright, so someone said opcodes. And bit assignments. Let's say bit patterns for instructions. Right? We have these 5 types of instructions: byte-oriented, literal, control, etc. Right? Why not have more or fewer than that? More I/O pins.
Different SFRs.
Different SFRs. What else? More memory. Our PIC has 256 general purpose registers. That's not a whole lot. And it only holds 2048 instructions. That's also not a lot. So we could increase that, or we could decrease it. We could say less memory. We could say fewer I/O pins. Well, we couldn't do fewer W. Well, we could do fewer W registers. We could say no W reg.
You could have more than 2 priority levels for interrupts.
Cool. More interrupt priority levels. So if you really kind of like sit back on a grassy hill and stare at the sky and just start thinking of the possibilities, right? Any particular processor is a really, really tiny point in this huge multi-dimensional design space, right? We can, always start at location 0 when we power up. We could always start at location 20 when we power up. And then we wouldn't have to constantly say 0, go to 20. We could have something that we could configure to say what address do we start executing at when we power up the machine. Speaking of power, doesn't have to be 5 volts. We could make the PIC run on 1.8 volts. We could make it so it would tolerate 9 volts, and now you could use a plain old 9-volt battery. We could make it run off of 12 volts. You could hook it up to your car battery, right? So the voltage range. We could adjust the speed. It defaults at a 32 kilohertz system clock. We could make that default different. It has a top end speed. Anybody know what the top end speed is for this PIC chip? Anybody glance around the data sheet at the clocking chapter?
Gigahertz.
It's actually 40. It's got 8 built in, but it'll tolerate up to 40 megahertz.
For like an external clock.
Yeah, from an external clock,
Okay.
which is pretty cool. That's like, 10 million pick instructions per second. That's kind of neat. And you can go as slowly as you want. And I keep challenging people in this course to like overclock a PIC processor. Nobody's done it yet, and now we're online, so it's hard to do it. But I want to see somebody like at least ice cool a PIC processor in the lab and see how much they can push the clock speed beyond 40 meg. So yeah, speed, voltage, more I/O pins, fewer I/O pins. What about the whole package in general? It's an 18-pin DIP. Dual inline package, 18 pins that look like the chips we use in 120, right? There's other packages available. There's things called quad flat packs that look like, little bugs with pins coming out on all 4 sides. So there's all kinds of decisions we can make. This is all part of what defines the architecture of any particular machine. Yeah, liquid nitrogen PIC, nice. This is what defines the architecture of a device. All right, so suppose you say, this is great, I want to make one chip to rule them all. Okay, I want to make the ideal chip, one that everybody's gonna buy. So what would be the general characteristics of like the ultimate take over the entire market of CPUs kind of chip? And I'll get you started here. Let's say we'd want it to be really high speed. We want it to be the fastest chip out there. What else? Affordable, right? Really cheap. Costs like a fraction of a penny. Alright, right now we've got most of the market share. What else could we do? What would be on your wish list?
Probably compatibility.
Okay, compatible. Let's make it at least compatible with Intel code, but maybe compatible with ARM code and PIC code and everything else. So super flexible like that. What else?
40 pins.
40 pins. How about 4,000 pins? At least 40 pins. Because we want lots of ways to get things in and out of our chip, right? With 18 pins, we've got all these multi-purpose pins. Is it RB3? Is it AN2? Is it a control pin, etc., etc.? So put lots of pins on the package. And they make chips with thousands of pins on them. They're not pins, they're little tiny solder balls sitting on the bottom of it. So good, nice, good set of connectivity options. All right, let's see, customizable. Someone said cooling, so low. Let's say low power, because it's the power dissipation that really means that you need cooling. Someone else said reliable. That's always a nice feature. And I finally see somebody said N pins. So yeah, lots of pins. Let's see, it's cheap, it's fast, it's easy to use, it's compatible, it's got lots of pins, it's low power, it's reliable. I'm going to say physically small. So we can put it in a smartwatch, And what else would be nice? I'm going to say low voltage. That kind of goes along with low power, but it's a little bit of a different one. Durable, yeah, so reliable, durable. Because if you're going to put it in a phone or a watch, you want to be able to drop it and run over it with your car and have it still work. So this is, you know, a good starting point for like the ultimate market killer chip. And if you could make a chip that really nailed each of these points, yeah, you'd have a really good device there. You want to go get some venture capital and start a new business and change the world, right? What's the problem with trying to do all of these things in one device? And I'll give you a hint. Can we do both of those things? Can we put in lots of I/O but still keep it physically small? Yeah, so somebody said trade-offs, right? Chances are any one of these things that you try to optimize is going to hurt a bunch of the others, possibly all of the others. If you want something to be really high speed, guess what? It's going to take a lot of power. You might be able to run it at a low voltage. In fact, that's probably better for high speed, but it's going to chew up power. The transistors that you need, the technology that you need to make a fast switch is very power hungry. And it's not going to be cheap. Right? CMOS is cheap because there's so much CMOS out there. There's lots of capacity to produce CMOS chips. ECL, which is what fast machines used to be made of, is very expensive to produce. And if you want it to be very cheap, it's probably going to have to be pretty simple, which means you're probably not going to build in compatibility with other machine languages. And it's probably not going to be really fast. And if you want it to be very reliable, it's probably not going to be too complex. And it's probably not going to be physically small, because the smaller your transistors are, the more prone they are to failure, the more prone they are to manufacturing defects, which raises your cost. And so my architecture teacher called this the N-way teeter-totter problem. Right? So like a teeter-totter or a seesaw, one person sits on one side and the other side raises up. And if somebody sits there, the first side raises up. Well, this is the same thing, but it's like in an n-dimensional space. And once you push down any one of these, all the others blow up. And so computer architecture is a question of choosing the right trade-offs. And there's no one solution for everything. If you're making a cell phone processor, you really, really want reliability and low power. Those are key. Because battery life's going to be your number one killer, and having the thing fail after 3 months of use, that's the end of your business, right? So low power and reliable are pretty major. Compatibility with other architectures, we don't care. Having lots of pins, we don't care. High speed, you probably don't care, right? The stuff that you can do on a CPU now versus the demands of a typical cell phone, it's a pretty easy trade-off. On the other hand, if you're building a web server for Google to use, you really want high speed. You really want lots of I/O capability. You don't care how much power you need. If you're Google, you go build a power substation, right? Definitely reliability. Physically small, space is something that can be bought. If you have, the inside of a mountain filled with your server racks, that's okay from a business perspective. Maybe not from an eco perspective, right? So depending on what it is you're trying to do, you make different design decisions. And that's part of computer architecture, is trying to figure out where the sweet spot is for a given market or a given application. And so x86 architecture, the stuff we were looking at a little while ago when we compiled that program, that's a complex instruction set. It's pretty expensive to design a new generation, which is why, you know, we don't see really frequent releases of new versions of Intel chips. It's very easy to program in some sense because the instruction set is very rich. And that's useful for things like laptops, desktops, right? Things that are going to stick around for a few years, things that are going to run the same software year after year after year, right? Most laptops are running the same stuff with some variations on them. Now a cell phone, very different situation, right? You need long battery life, you need reliability, you need to be physically small. That points to more of a reduced instruction set, a RISC architecture like what we've been doing with the PIC. So another aspect of computer architecture is how you work around this n-way teeter-totter problem. If I have a physically small device and I need it to be cheap and I need it to be easy to program, how do I get the speed up? And so we see things like pipelining, which we talked about a while ago when we looked inside the PIC processor. Pipelining, remember, was this idea that if it takes 8 steps to execute an instruction, right, 4 steps to fetch and 4 steps to decode and execute, what we can do is we can process more than one instruction at a time. And so while we're fetching our second instruction, we're decoding and executing our first instruction. And while we're decoding and executing our second instruction, we're starting to fetch our third instruction. And so even though it takes 2 of these 4 tick chunks to fetch, decode, and execute an instruction, our throughput is basically 1 instruction gets decoded and executed every time that our instruction clock ticks. Okay, so that's pipelining. And we talked about pipelining. With a 2-stage pipeline, you effectively double your throughput. With an 8-stage pipeline, you get 8 times your throughput. And the performance killer is when you have to stall. When, for example, you fetch the wrong instruction, and after you finish decoding this one and executing it, you say, oh, I'm supposed to be fetching from a different location in memory. Now this instruction is invalid and my pipeline is empty. And I have to wait 1 instruction tick to fetch and then another instruction tick to decode and execute. And this is part of the reason that clock speed is somewhat of a marketing term. So if you go into a box store and you look at laptops, right, probably the first or second thing you see on the information card is the clock speed. Right, 2.4 gigahertz, 2.8 gigahertz, 3 gigahertz. But it's a bit of a marketing thing. All that a 3 gigahertz clock tells you is that there's 3 billion things happening per second. But unless you know what those 3 billion things are, you don't know if that's good or bad. So if you're multiplying a floating point number by another floating point number and getting an answer 3 billion times a second, that's really good. Okay, if 3 billion times a second your state machine's clock is ticking, and it takes 20 state changes to add 2 numbers together, that's not as impressive. Yeah, you're doing 3 billion things per second, but how many numbers are you adding per second? 200 million. But you don't want to sell a computer and say 0.2 gigahertz, right? So we talk about clock speed. All right, this ties in a little bit to memory. So, PIC processor memory is simple. There's 256 general file registers. There's about 64 special function registers. And there's program memory. My laptop has 16 gigabytes of main memory. Okay, 16 gig, that's 16 billion bytes. That's 128 billion bits sitting on my memory cards in my laptop. Okay, suppose you have a 3 gigahertz clock. So how many things are we doing in 1 second? We're doing 3 billion. Billion ticks per second. So how long is the period of a single tick? What's the time equivalent of this frequency of 3 gigahertz?
Oh, 1 divided by 3 billion?
1 divided by 3 billion. Okay, 1 billionth of a second is a nanosecond. So 1 3 billionth of a second is a third of a nanosecond. Alright, how far does an electron move in a nanosecond? This is a good metric to know. So Grace Hopper used to give lectures on computing, and she would hand out nanoseconds, and they were little pieces of wire that were 12 inches long, right? So about that long. That's how far an electron can move in a nanosecond. So in a third of a nanosecond, we're talking 4 inches. That's it. That's the physical distance an electron can move in 1 clock tick on a 3 gigahertz machine. So suppose you look at your motherboard, and here's your CPU, and here's your DRAM. How close do those have to be to each other to be able to read memory in a third of a nanosecond? Well, the CPU needs to send a request to the DRAM needs to send it back. Assuming that the DRAM responds instantaneously, it's got to be within 2 inches of your CPU. The furthest part of your CPU and the furthest part of your DRAM have to be within 2 inches of each other. Well, you know, most chips today are at least 2 inches across anyway. We can't even move a signal from one side of the chip to the other in a third of a nanosecond. And if you want to go off your chip and go over to another chunk of chips where your memory is, send a request, get it back, right? It's not possible. You can't do that 3 billion times a second. That's just a physical distance limitation. But besides that, getting a signal out of a chip onto one of those silver lines that you see on your motherboard, well, they're green, they're covered with a coating. Getting your signal out of your CPU onto one of those lines on your motherboard and then getting it back into another chip, that takes time, right? Because we have really low current inside our CPU, but we need really high current to move a signal across the motherboard. And decoding your address once you get over here, finding the piece of data that you're looking for and presenting it on some lines to go back to the CPU, that takes time. So if we need our CPU to go out to our main memory, it takes way more than a third of a nanosecond. It's like frightfully slow. Okay, so we're talking about memory organization here. So here's an analogy. Suppose you work at a library. So you're sitting at the front desk of the library, and this library has 1 million books. Okay, 1 million books. And each book has 200 pages, and each page has 80 words written on it. Okay, that's a total of 16 billion words. So that's on par with our dynamic RAM. So you're sitting at the front desk of this library, and your job is when someone comes up to you, they're going to hand you a piece of paper and say, hey, I'm looking for this word. And they're going to tell you which book it's in, which page it's on, and which word it is on that page. And you take that piece of paper and you go back into the stacks. Now, 1,000,000 books, right? This is a lot of physical space, so you have to walk really fast, get back into the stacks. If the book's on an upper shelf, you got to pull the ladder over and climb up there. You pull the book down, you open it up to the page number, you count down the right number of words, you find the word they're looking for. Let's say the word is cat. Okay, you write that down on a piece of paper, you put the book back on the shelf, you run back to the front desk, and you hand the person the piece of paper with their word cat. Alright, so someone comes in and they say they want book 237,193. They want page 74 and they want word 12. And you do that and it's cat. And you hand them that word and they're like, thank you very much. And they walk away. And a moment later they come back and they say, okay, I'd like book 237,193, page 74, word 13. And you go back in the shelves, and you pull the book down, you flip to the page, you look at word 13, and it's the word says. And you write that down, you bring it back, and you hand it to the patron. And a moment later, what do? They come back to you and they say, I want this book, this page, I want word 14. And you go back in the shelves and you do the same thing. You look at the word and it says meow. And the person does this to you another 50 times. Is this annoying? Right? This is not a fun job. This is the life of a CPU. This is the life of a memory management system. The CPU comes in and it says, give me the 8 bits at this one location out of 16 billion. And you have to find the book and the page and the word number and write it down and bring it back. And then the person turns around and says, oh yeah, I want the next word too. And then maybe this person's slice of time is up and somebody else comes along and they have a different book and a different page and a different word and they ask for that. And you go back and you find that and give it to them. And then they come back a moment later and they ask for the next word on that page themselves, and so on and so forth. So how do you deal with this? How do you minimize how much time it takes to satisfy these customer requests? What's the easy thing that you can do knowing that this is the way that customers treat you? They tend to ask for consecutive words.
You could like have a cache of like a bunch of words.
Yeah. So I don't want to actually take the book out. I don't want to rip the page out of the book. But I'm going to copy down every word on that page. So when they ask for, word 12 on page 74 of this book, I'm going to take the book off the shelf, I'm going to flip to page 74, I'm going to take my portable copier and I'm going to make a copy of that page. I put the book back, I walk forward to the front desk, and I've got a sheet of paper now that has every word on page 74 of that book. And I hand them the word cat. Well, then they come back a minute later and say, I want word 13. I make sure it's the same book and same page. I don't have to go back to the shelves again. I just look at my sheet of paper and I say, oh yeah, word 13. And they can do that, until they run out of all 80 words. Now if they want a word on a new page, now I got to go back into the shelves and I got to make a copy of page 75, and then I'm good for the next 80 requests. Okay? That's a cache memory. So that's what cache is all about. We make a local copy and we keep it with us so that when somebody asks us for something, we don't have to go to the original source. We've made a copy of it. So the CPU is the customer, right? You're executing an instruction that wants to read a number from an array, and it's going to talk to the memory management unit. That's me, the librarian. And the first time that it asks me for something, I've got to go to DRAM. I've got to go all the way across the motherboard. It's going to take a long time. The CPU is going to stall. It's going to take, dozens of clock cycles where nothing is happening because I'm walking back to the main memory trying to find this information. But when I come back, I've got a local copy of a bunch of locations stored around the one that was saved. The one that was asked for. And the next time that I get an instruction, like, okay, give me the next location in this array, I've got it in my local copy, and I can just hand it right back. And I can do that quickly enough that the CPU does not have to stall. The clock will keep running at full speed. My pipeline will stay full. My throughput stays high. Everybody's happy. All right. Well, I've got, a few hundred customers. And even though somebody has gone on from page 74 to page 75, they might come back and eventually want this particular word again. Because what do we do with arrays sometimes? We iterate over them. We start at the beginning, we move through the array, and we do some processing, and then at some point we go back to the beginning of the array and we start again. So we don't necessarily want to forget this page of values that we had just because somebody's asking for a different page. So we want to keep it around. But if I've got hundreds of customers coming in throughout the day and this library never closes, and so days turn into weeks, turn into months, what ends up happening? I have a really big stack of sheets of paper. My cache is getting really, really big. And if this goes on long enough, eventually I'm going to have the same problem I had in my original stacks. I'm going to have to start, organizing these sheets of paper in some way. I'm going to put them into books. I'm going to put them into bookcases. I'm going to end up with, millions of sheets of paper. So we have to limit how many pieces of paper we're going to have in our cache. Cache size is very limited. Now your main memory on a laptop could be 16 gigabytes. Your cache memory is going to be megabytes. Okay, many orders of magnitude smaller. Your cache memory also is going to be expensive. Cache uses a different kind of memory architecture. Main memory is something called DRAM. The D is for dynamic. Dynamic as in changing. Dynamic as in if you load a value into the DRAM and you just leave it, that value will disappear very quickly. You have to periodically go through all the information stored in your DRAM and refresh it. It's stored on a bunch of little capacitors, and those capacitors dissipate over time. Cache uses what's called static RAM or SRAM. These are flip-flops. Very expensive. DRAM you can do with a single transistor. Flip-flops you need several transistors at least. Much faster, but very more expensive. So cache memory is really small. So what do we do with this fact that we're getting more and more pages that we've copied from our books, and we can only have a certain number of these? Well, we'll just put a limit on it. We'll say I'm only going to keep 50 pages at a time. And I'm going to use a clipboard, and every time that I get a new page, I'm going to put it on the top of the clipboard. And then when someone comes to me and they say, hey, I'm looking for a certain book page in Word, I have to flip through, up to 50 pages to see if I've already got that page. And if I do, I'm going to take it, I'm going to put it on the top of my clipboard, and I'm going to give them the word that they asked for. When I find that I need a 51st page, what am I going to do? I'm just going to get rid of the bottom page from my clipboard, because that's a page I haven't used in a long time, because when I use a page, I put it on the top. So that's something called LRU replacement, least recently used replacement. And there's lots of strategies for keeping track of LRU, of when a page has been used. And a common strategy is whichever page you haven't used in a long time, get rid of that if you need more space. All right, so yeah, question, is that why SSDs vary in price so much? SSDs are interesting. So yeah, they might have some caching on board. But SSDs, I think there's just a lot of variation in the technology that's used, as well as the interfacing. So if it's most of them use what's called NAND technology for flashes, for flash memory. I don't know the physics of it, but there's different ways to create this non-volatile memory. Some of it is very fast and expensive. Some of it is less expensive but slower. Some of it has to do with interfacing, right? So if you can interface with USB-C or with an ATA interface, that's going to be more expensive than a USB 2.0 or a USB 1 something. And I'm guessing reliability. I don't like to think about that because I got an inexpensive SSD for my machine. But yeah, cache is probably one of the factors in there. Alright, so we can throw away pages when they haven't been used in a while and our clipboard is full. We've got 50 sheets in there already. And so these are all things that happen in cache memory. Now it gets really wonky if you actually allow your customers to write in the books that they're making requests from. If a customer can come up to you and say, okay, I want to make a change in this book. I want you to change this book, page 74, word 12, to be dog. Well, without a cache, what do? You run back in the stacks, you pull down the book, you flip to that page, you count to the word, you scratch out the word that's there, and you write the new word. Okay, how does this work with caching? Because on a computer, we do a lot of reading, but we also do a lot of writing. And if the writings are going slow, you've got a problem. So how does this work with caching? Well, I've got a sheet of paper that I made a copy of page 74. How about on that sheet of paper, I scratch out word 12 and replace it with the word dog. And now if the customer comes back later and says, hey, can you give me word 12? I look at my sheet of paper, it's got the word dog. That works great. Where do I get into problem though with this strategy of doing my updates on this piece of paper? What's the big performance issue here?
It leads to cache.
Yeah, so when I'm done with that page, when it's at the bottom of the clipboard and I decide to get rid of it, if I'm not careful, I get rid of the changes that this person made because the original book back on the shelves still says cat. So at some point, these changes that I'm making on my piece of paper need to get written into the original books. Okay, this is another cache problem. We have our main memory, our DRAM, and then we have this local copy of it. Okay? When the CPU makes changes to memory values in this local copy, they need to get synchronized to that dynamic RAM somehow. And there's two main approaches to that. The first approach is that when the person says change this word to dog, I go ahead and I change it on my sheet of paper, and I also run back into the shelves and I change the actual book. Okay, that's a strategy called write through. I update the cache, but I also update the original memory. That's inefficient because my cache is doing great for reading information, but every time I write, I have to pay the same performance penalty of actually going out to the main memory. So our more common strategy is write back. And write back simply says, when I take that page off the bottom of the clipboard and I'm about to throw it out, I check to see if I've made any changes on it. And if I have, then I walk back into the shelves and I make all those changes at once. That's a lot more efficient. Because you might change the values in some locations in memory, a million times. And if you just keep making those changes in cache, that's very efficient. And then at some point, your process goes away, you haven't touched those locations in a while, we need more space in the cache. Now I pay this one-time penalty of taking the latest values of those changes and writing them back into the main memory. So that's much more efficient. But you got to be really careful and make sure you don't throw away that page without writing those changes. All right, when does this become a problem? In main memory, if something catastrophic happens, if the power goes out and my CPU crashes, the fact that I've got some things in my cache that haven't been written out to main memory, not a huge problem. Because once the CPU loses power, the memory gets erased anyway. But here's a bigger problem. A flash drive. So flash drives are really slow to read from and write to. Okay, they use technology that is non-volatile. You can remove power and it remembers the bit values, but there's a performance hit. Okay, pretty slow to go out through a USB port and address the bits in here and update their values. So we use caching when we deal with flash drives. You put your flash drive in your machine and you read values from it. Any values that you read get saved locally in memory. And when you want to write a value to your flash drive, instead of going out and paying the penalty of actually writing to this, I update the cache, the local copy of it in memory. It's a much more efficient operation. This is how you get flash drives that you can work with at a high speed. But guess what happens if I lose power? If I'm doing write back, I'm making write changes to my local copy, and I'm planning to write them to this drive eventually. But if I lose power, I don't get a chance to write that cache into here. This can become corrupt. Similarly, if I've got this plugged into my drive and I need to go somewhere and I just pull it out and I'm using a write back strategy, this has not got valid information in it anymore. I've got changes I made in my cache that have not been written to here. And the next time I plug this in, guess what? It's going to notice that there's corruption and I may have lost my data. So this is this whole notion of safe removal, or optimizing for performance versus optimizing for fast removal. So if you set up your drive to say I want to be able to do fast removal, you're asking for a write-through strategy. So that when you make a change to something that's stored on the drive, it gets written out immediately. It's not as efficient. But it means that at some point if I pull this out, it's got correct information on it. If I optimize for speed, I need to do this eject procedure, and what the eject procedure is doing is all of the write-backs. All the pages in cache that have been modified are getting pushed back onto the physical device, and that can take a long time. If you've been doing a lot of writing and you've got a really good cache system, this can take a minute, right, before it actually lets you eject it. Alright, so caching is a whole nother field. You can do a whole career just dealing with cache memory. It's a huge aspect of computer architecture, and it's its own n-way teeter-totter. There's no one solution that works best for all situations. But you know, how big a cache do you want? How big a page do you want to copy from the book, right? Maybe you only want to Xerox a single page from the book, but maybe you want to copy, 10 pages. Maybe you want to copy the entire book when somebody requests anything from it, right? So this is the page size. On a computer, when you access a location in memory, that location gets cached, but so does a whole bunch of other values before and after that location. So it pulls in a whole page from memory. DRAM is slow, but accessing a page of consecutive locations can be very fast. These are more tricks that are used in memory design subsystems. And the usual setup is, here's your CPU. Your cache is actually sitting on the physical CPU chip. If you look at pictures, electron microscope pictures of what's inside a CPU, you usually see a big section that looks very uniform. Chances are that's a cache. And cache is expensive, and so it's generally small. But you can have levels of cache. So we can have a cache with modestly affordable technology, and that could be fairly big. That could be 16 meg. That could be an L1 cache. And going to an L1 cache might not be something you can do in a single instruction tick, but maybe you can do it in like 4 instruction cycles. But we can put another cache around this first cache. For things that we access from here frequently, we could have a smaller cache that's fast enough to keep up with our 3 gigahertz clock, and that would be an L2 cache. Actually, L1 would be the fast one, I think. L2 would be the slower one. But we can have this hierarchy of cache. So we've got our main memory, and then we've got levels of cache memory. And then inside the CPU itself, there's usually registers, which are different from picked registers. There's usually like, 12 registers that are extremely fast access and general purpose. All right, so let's take a break here. We'll come back. I'll talk a little bit more about memory. I'll say a few things about concurrency, and we'll call it good after that. Take about a 5-minute break. We'll come back and finish this up. All right, last and final piece of all of this. So let's look at the other. All right, last and final piece of all of this. So let's look at the other direction of memory. 16 gigabytes of main memory sounds like a lot, and computers used to have 16K of memory, and the really big ones had 64K, and 64K, that's 2 to the 16th. Architecturally, early CPUs weren't made to address more than 2 to the 16th locations, so 64K of memory was pretty significant. Well, 16 billion should be, more than enough for anybody, but it's not, right? Code is so large and the data sets we process are so huge that we need more than a few gigabytes of memory. And if you're doing like scientific processing, if you're trying to invert a really large matrix, solve a large system of equations simultaneously, etc., you may need, hundreds of gigabytes of information that your CPU can access. So most of our larger machines, so pick processor, right, location 80 is location 80, location 0 is location 0. But most larger machines, x86 machines, for example, use what's called virtual memory. And this is basically an extra layer of translation. So your CPU wants to ask for and modify information at certain locations in memory. But between the CPU and the physical memory is this intermediate layer that basically converts addresses that the CPU knows about into actual addresses in the physical memory. So a typical program might say always start at location 0 in executing instructions. It's always going to want to say, give me the instruction at location 0. Well, if you have 20 programs that all want to store their first instruction at location 0, and they're all directly addressing the physical memory, right? Which one are you going to actually store at location 0? You end up having to move stuff in and out so that when my program's running, I can put my instructions in this part of physical memory, and then when you want to run your program, I've got to somehow take all of my instructions, save them somewhere else, put your instructions into memory, and then let your code execute for a while. And that's expensive. So instead, we have this translation mechanism so that the CPU thinks it's working with, say, address 0, but in fact, address 0 might be down here in the physical memory. So maybe that's where my process is storing address 0. And your process maybe stores address 0 up here. Now when my process is running, all I have to do is set up my translation system to know, hey, when you ask for address 0, use this location in physical memory. And then when it's time for your process to run, all we got to do is change this translation to say, hey, when you ask for address 0, go to this location in physical memory. All right, so we're changing this translation system instead of moving things around in physical memory. So the addresses that the CPU are accessing are actually virtual memory addresses. And there's a number of good reasons for this. One reason is this ability to relocate where things are in physical memory. Even though, maybe I want to write my interrupt code at location 8, it doesn't have to go at location 8 in physical memory. It goes at location 8 in my virtual memory. And this translation may simply be, take the address that you want and add some magic number to it. And that magic number tells me how far down in my physical memory to start. So that's one advantage. Another advantage is security. If there's nothing in this translation mechanism that lets your process get to these locations, then I have, an architectural level security measure against your being able to read my data. You can make an array that overflows, you can do buffer overruns, but if your addresses always translate to things, say, in this range of the physical memory, and my translation maps to things in this range, at an architectural level, there's no way that you can write code that will interact with my memory. So you can't read private information, you can't change flags, you can't put in, trapdoors and things like that. So it's a security measure. Another advantage of virtual memory is size. And this is one of the bigger ones. This is one of the more often used ones, right? The fact that my physical memory might be 1 gig, but my virtual memory might be 1/4 of a terabyte. And what do I do here? Well, chances are when your program is running, you're working with one section of memory for a long time. We're reading an array and analyzing it and updating it. And then at some point, maybe we start working with another array or a different section of the array. So when we're working with one section of this 256 gigabytes of memory, we can map that to some chunk of this physical memory. And then if I want to access some location of memory that doesn't map to anything in my physical memory, I change the mapping. And so we start to have something like a page file, which is stored on our hard drive. And part of your virtual memory is actually stored on your system's hard disk. So if you find a swap file, right, that's what that's about. Or a paging file, it used to be a pagefile.sys under Windows. That was part of your virtual memory system. And so this is a hierarchy in the other direction, right? We have physical memory, but that actually gets managed by a virtual memory system, which can include, storage on your hard drive. And your hard drive, is terabytes, possibly. And so plenty of space for having a really large virtual memory. And the virtual memory is in some sense, our physical memory is almost like a cache into our virtual memory. All right, this gets into lots of interesting performance issues because suppose I say something like increment file register 80. Right? How hard can that be? Read the contents of file register 80, add 1 to it using my add circuit from Engineering 250, and then write the result back into file register 80. Okay, so on a non-PIC processor, this is memory location 80. Well, the CPU is going to look to see if this has been cached, and if it has, it's going to do this immediately. It's going to update the cached copy, and it's going to set something up so that eventually that new value gets written back to memory. So it's going to check my first level cache, and if it's not in there, it's going to check the second level and the third level, and if it's not in any of my caches, it's going to have to actually read this from physical memory. Okay? It's going to go through a translation. And that translation might say, okay, file register 80 is stored right here in your physical memory. So now it's going to make the really expensive request, right, to the librarian who's got to run back into the shelves and pull down the books and all that kind of stuff. So this will take, you know, dozens of clock cycles. But it's possible that we've got so much stuff in our virtual memory that file register 80 is not stored anywhere in our physical memory. It's stored in a file on our hard drive. And now what's going to happen? We're in the middle of this increment file register instruction. The operating system kicks in and says, hey, wait a minute, we got to change around what's stored in physical memory. It's going to have to figure out some chunk of physical memory that hasn't been used in a while that it can get rid of. And it's going to make sure everything's up to date, and it's going to figure out where in the page file this chunk of memory should get written, and it's going to write it. Well, how do you write from main memory into a disk file? Well, you've got to do millions of instructions, right? You've got to open this file, you've got to talk to the spinning disk and the moving read-write head, and somehow figure out when the right time is to start writing ones and zeros and send those out into this file, right? And all this stuff is security managed and everything else. And then when you're done, you've got to get to where memory address 80 had been stored in this page file. You've got to read a whole page out of that, adjust your translation, write it into your physical memory, all so that you can go back and try again to execute this instruction. This is like the most severe kind of interrupt, right? This is not happening at the end of an instruction. This is happening in the middle of an instruction. This should take one instruction cycle. It's probably taking about 1 million. So we tried to increment. We found that this wasn't available. It generated what's called a page fault. And it's basically a software interrupt. And it happens in the middle of an instruction that says, anything you've done, undo it. Let's go back to before we began to execute this instruction. I need a minute, don't bother me. And the operating system will go off and it will do all of this remapping of memory. And in the end, it will set things up so that memory location 80 now is stored somewhere in your physical memory. And now it'll say, okay, we subtracted 2 from the PC, let's go ahead and re-execute this instruction. It returns from the interrupt, and your CPU says, oh, let's increment file register 80. So it makes a request for location 80, it gets translated into a physical memory location. Oh yeah, it's stored right here. It pulls that off, it loads it into cache, it gets incremented, and you're good to go. Now if your next instruction says increment address 81, that's immediate, it takes 1 cycle. Because in addition to loading 80 into your local cache, it also stored a whole bunch of locations after that and before that. But these page faults are performance killers, right? And they'll not just stall your pipeline, they'll actually generally cause your whole process to get swapped out of memory. And while the memory subsystem is doing all of this stuff, somebody else's job is running in the CPU. Okay, so I go through all of this for a few reasons. One, it's part of the course material technically, even though it's not on your exam. It's stuff that you're supposed to see in this course. 2, I think it's interesting to know what's actually going on. And so it's worth mentioning for that. But 3, it's a classic example of where hardware and software are not really separate independent things. Right? Increment file register 80, that's a purely software notion. Read this, add 1, write it back. But to understand everything that could be happening when you do this one instruction, You really need to understand the hardware. And you need to understand the operating system. And you need to understand how memory works and how memory hierarchies work. And all of these different aspects are intertwined. And it used to be, you know, you had a CPU that executed instructions. You had a memory that you could write to and read from. You had an operating system that would run programs. You had a compiler that would convert code into ones and zeros. And, you know, you could have separate teams of people working on each of those things. Those days are long gone, right? Those went away back in the VAX 780 days or before. And everything is so integrated. Everything is so tightly bound with everything else. And as a software person, you sometimes need to understand what's going on at the hardware level. When you're writing interrupt-driven code, event-driven code to make GUIs, to make games, things like that, you need to have some understanding of how interrupts are working. If you're a hardware person, you're designing a CPU, you need to understand how the software that's using that CPU is going to be written. You need to understand that when you have a two-dimensional array, it's stored linearly in memory, because memory is linear. And if you store that array by going across and slowly moving down, it's important to know that when you try to access it. Because if you have an array two dimensions, and let's say it's 1,000,000 by 1,000,000. Alright, 1,000,000 by 1,000,000 array of floating point numbers. Pretty small problem for a lot of scientific computation. So 1,000,000 things across, 1,000,000 things going down. 1,000,000 times 1,000,000, that's 1,000,000,000,000 numbers. Okay, so a tera number. If your numbers are 4 bytes, it's 4 terabytes of data. Alright, this is stored sequentially in memory. And it can be stored in one of two ways. The usual way is row major, where we store the entire first row, and then we come down and we store the second row, and so on, and eventually we store the last row. So in memory, this might be location, 20, 21, 22, all the way up to, 1,020, 1,021, 1,022, all the way up to 2,020, and so on. Well, let's say I want to add up all the elements in this 2x2 matrix. If I start up here in row 0, column 0, and I move across my row and keep adding up numbers, that's going to be very efficient, because when I fetch this element, my cache system is going to say, hey, let's fetch, the next 500,000 numbers also. And all of these reads from memory are going to be cache hits. And then somewhere out here I'll get a cache miss. It's expensive, but then I filled in like a whole bunch of other locations. But suppose instead I decide to go through my array column major. I decide to read this entry, and then this entry, and this entry, and this entry, and this entry. This is just a change in the order of my for loops. Putting for j equals instead of for I equals first. Well, what happens? I access this first location in memory, and my memory manager fetches a whole bunch of locations for me from cache, all of these locations. Well, this next location I access is 1,000,000 times 4 bytes away from that first one. And it's another cache miss, and it's expensive. And the CPU memory management combo fetches another 500,000 locations for me. And then my third access is 1,000,000 locations times 4 from my first. It's another cache miss. I'm going to miscache every one of these trillion accesses that I make. And my nested for loops for adding up the elements in this array just got, 50 or 100 times slower, simply because I switched the order in which I use I and j in accessing my array. Right? That's something that requires understanding the hardware, understanding memory, understanding cache strategies, even though all I'm doing is I'm writing a pair of nested loops for I equals, for j equals, sum equals sum plus data bracket I bracket j. And if I write this in a different language, that language might store things in column major form. And so now I'd want to say for j equals, for I equals, data equals data plus, or sum equals sum plus data bracket I, comma j. So the moral of the story is really just that everything is interrelated. And whichever way you're heading, whether it's hardware, software, game design, embedded systems, application programming, right? The more you know about all the different pieces of the system, the better off you're going to be. Right? And it can make the difference between writing something that works and writing something that works really, really well. Alright, we're supposed to cover concurrency. I'm not going to talk about concurrency. It's a huge topic. You can read about it in the book, but you'll encounter it in other courses if you're software rooted. It's basically the question of, one CPU does things pretty fast. If you have two CPUs, can you do things twice as fast? And to some degree, that's true. But if you had 1,000 CPUs, can you do things 1,000 times as fast? Probably not. Right, so there's trade-offs, and the question of how do you effectively utilize multiple processors or maybe multiple cores inside a system, that's part of the topic of concurrency. We're also supposed to talk about networking. If you're CS, you've heard me talk some about this in 223. But networking is another hierarchical system, just like memory. We have a low level where we have actual physical phenomenon conveying information, and we put layers on top of that to be able to interpret this in different ways, with a top layer being something like, sending an HTTP request to a web browser, a bottom layer being something like, let's modulate a 2.4 gigahertz wavelength signal to convey wireless information using a standard called 802.11, which is another IEEE standard. All right, so I think we're good for Engineering 270. Any parting questions, comments, concerns?
This will be a quarter to remember.
Definitely, in a lot of ways, I suspect. So this stuff on cache memory, computer architecture, virtual memory, concurrency, all that stuff, none of that's on the exam. Okay, that's all freebie material. But it's worth taking a quick read through the book anyway, and asking questions if you like. But like I say, depending on what you're studying after this, you'll encounter different aspects of this to different degrees. Alright, I will switch to office hours. I'm not going to go to my office. I'm going to stay in the 270 room until class ends at 3:50. So if you have questions or things you want to go over, or if you're working on labs and want to talk about lab questions, I'm just going to stay in the Zoom room that we're in right now. Okay, I'll mute my microphone and kill my camera, but otherwise you're free to carry on. Thursday, 12 o'clock will be the final exam. It'll start at 12. It'll open up automatically on Canvas. I'll be in Zoom for the duration of that. I should be reachable by email. You can also chat with me, and so on and so forth. And I'll leave the quiz open for 3 hours as the base time. All right. Well, thank you everyone for your energies. I know people have worked phenomenally hard in this course. The number of questions that I'm getting in email and the nature of the questions are making it pretty clear that people are working really hard. And it's a tricky system being online, and a lot of people are taking 2 or 3 courses this summer. Some people also started WSU this week. So I really appreciate the effort people have put into it. Hopefully you gotten some useful stuff out of this. Catch me in Zoom. Otherwise, I will see you on Thursday. Have a great rest of the day, rest of the week till then. And thanks.